I will discuss on the hypergeometric type function and the properties. Basically, here we are in this talk. We have given the two sections, section 1 and section 2. This based on both the work of my PhD student, Snehal Virao and Gumtam Heswari. So here we developed this work. This is extended the work of Vanchenko, and she given the generalization of the hypergeometric function. So first we have to start. So these are the outlines of this my talk. Introduction, extended tau hypergeometric function, some property of extended tau hypergeometric function, extended incomplete tau hypergeometric function, extended cosine symbol and associated extended hypergeometric function, asymptotic expansion and extended convergent hypergeometric function, conclusion and the future scope. And this is the first this is introduction to the special function and the hypergeometric function, and some extension of the hypergeometric function given by some different authors. Most importantly, what are the special functions? And we cannot forget the work of Madhava, and he belongs to Kerala, and during, I think, as per my memory, I think 11th, 12th century, trigonometrical series, and this given the value of the pi in the form of the series. This credit goes to him, Madhava, but later on this work has been given by different authors. I think Gregori series is also one of them. He also worked some Gregori type series during, and that was some modified version. Gregori giving some modified version of that series. And here Newton and Leibniz discovered the subject. And numerical mathematicians have contributed to like to the field, like Ramanujan, Euler, Fourier, Legendre, Laplace, Gauss, Maxwell, Kumar, and Einstein, and Riemann. First, we will discuss about the Euler power series. The power series is given like this: 1 plus a dot b divided by c dot 1 z a plus 1 dot b plus 1 z square divided by c plus 1 and 2. So basically here, so where a, b, c are the decimal parameters, and basically this series that are known as the hypergeometric series, because if you see, so the series can be converted in the form of this geometrical series, or we can say the geometrical series is a special case of this hypergeometric series. And next, why it is called the Gauss function, and research so many contributions made by the Gauss and property obtained by the Gauss. So this is totally also known as the Gauss hypergeometric function. Earlier it was given by the Euler, and this this hypergeometric function, this we have just now discussed about the hypergeometric function. If we take like this, suppose that equation number 1. So this is known as the hypergeometric function, and here this is convergence condition. This mod of z is less than 1, and here this mu1 is not equal to 0, -1, -2, -3, so on. And here the cosine symbol defined. This is a lambda by mu. This is a gamma lambda plus mu divided by gamma lambda. So here this is 1, and this is equal to 0, and this equal to 0, and using the condition, this lambda belongs to C, excluding 0. Similarly, here this the gamma lambda given by gamma lambda plus 1, lambda plus 2, lambda plus 3, up to so on. So this is lambda plus n minus 1. So finally, so here this mu belongs to n, and this lambda belongs to C. That is a complex number. And here this gamma function. So this gamma function is defined as equation number 3. This is well known. All of you are familiar with the gamma function, are very much useful in the field of the mathematics and applied mathematics and fractional calculus. So basically, if you see the fractional calculus, basically the credit goes to development of the fractional calculus, credit goes to gamma function also. And here, generalize the hypergeometric function that is given as equation number 4. So here we are having a two FN series. Two FN series with 2 parameters in the numerator and 1 parameter in the denominator. Okay, and here we are having the 3 parameter in the numerator and 2 parameter in the denominator. Okay, and define or you can say the extended generalized hypergeometric function in the equation number 5. So basically, put all this in the form of the gamma function. In place of in place of then we are using this the Poisson symbol. So he basically used the gamma function, and that is given by this. And here condition, both the condition with this 1 plus this mu t, the t 1 to q minus r equal to 1 to p, br is this. So it means here you can say this. It means your value this mu1, mu2, mu3, mu4, mu5 like this. So these are greater than this. It means greater than this your b1, b2, b3, b4, b5 up to b3. So finally, it means this is very most important condition and defined as equation number 5. And here special generalization that is given by the hypergeometric function, and this is into form of this. So here we some parameter introduced. This is the mu and the omega. So they put like this. So basically, if you see, so this is nothing as simple, just like your right type hypergeometric function. So it is your mu is this. So it means mu1 is this. So ultimately that becomes here in the denominator mu1 going to this omega upon mu, and okay. So it means so they can put into this form. So this is one type of the hypergeometric function, or you can say some right type. And next one is 2001. This Varchenko defined this right type hypergeometric function by taking this omega upon mu equal to tau, this equal to tau, which is greater than 0, and she defined this equation number 7 as it's like this. So basically here you will see these two parameters are in a gamma function, and one this is in Poisson symbol. And recently Parmar introduced extension with tau type hypergeometric function, that equation number 7, and he defined as equation number 8, and by imposing the condition, and also this is some new type of the Poisson symbol has also been defined by him as an equation which is mentioned as equation number 9. And further, this Chaudhary and Jubair also defined this new type of the gamma function. This is extension of the gamma function, and that is defined as equation number 10. So here they take suppose here they took this t raised to power z minus 1 exponential minus t upon p. So basically they introduce this minus p upon t. So minus p upon t. So if we put the p equal to 0, then ultimately this would be converted into gamma function that is mentioned here. This is equation number 10. Next, in 2014, Srivastava, that is Rekha Srivastava, introduced to study the following family of generalized hypergeometric function. So he took the pair of like this. So rho 1 and this p, first one, and this p1, p2, p3 like this. So it means they only by say include this much. This rho 1 p, that is equation number defined as equation number 11, and here conditions are no denominator parameter is 0 or negative integer in equation number 11, and provided that the series of the right hand side of 11 converges. Okay. Now we will discuss some extended tau type hypergeometric function. So here in the tau type hypergeometric function, this is a first extension of the tau right type hypergeometric function. We obtain generating relation, continuity relation, differential and integer property, and the difference formula. So here we introduced an extension of the Bursaid-Co right hypergeometric function as this. So here we use this. So basically this concept given by the Srivastava. So we use this concept, and here we extended this one as equation number 12 by imposing all the conditions, that is condition which I mentioned here, and in terms of generalized extended Poisson symbol 19. So this is given by this one. This is given by the H.M. Srivastava. This is equation number 30. And equation number 30. Next, the function is this function. This is a extension, an extended gamma function, and this has been defined. This has been defined as equation number 14, and appropriate to the bounded sequences. This is the bounded sequence of the essentially arbitrary real or the complex number. This function is due to Srivastava, and this has been as mentioned as equation number 15. So here we use these symbols like this. So it depends on this L K L, and this L belongs to L. Compose this, so it is given into this form. And we put this into form of this integer representation, because as you know, in a spatial function, integer representation is very important. If you have any function, if you generalize any function, if you introduce any function, the function of polynomial, that should have a integer representation. And this is a very interesting component in the field of the spatial function, the theory of the spatial function. So we also obtain this integer representation of this function, and this is given into this form. This is as equation number 16. So here if you see, so all the conditions this here that have been mentioned. This is a real part of this mu1, and the greater than real part of this rho 2, which is equal to greater than 0. So this is a greater than this rho 2 as well as the real part of this, and this is also greater than 0. And this we can also use this by using this concept, and property of the beta function here. So we can obtain this integer representation of this function. And here the generating function, and after the integer representation, we obtain the generating function that is defined. The following generating function and hold true for the extended tau right type hypergeometric function. And there are two R1, this is tau. So we introduce actually this tau parameter. So as defined as equation number 12. So this one, so it means here we can obtain this generating function of this of the given this hypergeometric function. So provided the condition, we impose the conditions are here, provided both the member of each generative function 17 and 18 exist. So basically here we have to take care about the convergence condition. If we fail to do it, then it is totally becomes meaningless. So it means, so here due to this reason we impose all the conditions accordingly. So here for the proof of this, so one can easily obtain by using this binomial coefficient, and this expression can be put into this form, and finally we arrive at this conclusion. And similarly, we can also obtain the second theorem. This is the second, so this one, the second result. second result can also be obtained by using this concept. And here some relations, we also obtain some relations. That is as equation number 19 and equation number 20 and equation number 21 and equation number this is 22. So it means this is here 19, 20, 21 and 22. So here we give some proof of this theorem. So this is by putting this value and using the definition of G generalized binomial coefficient as earlier I discussed in our last slide. And this is an extended tau right type hypergeometric function, and involving the order of solution, we obtain our decision. So same method can be applied for obtaining this 20, 21 and 22. So all this one clear. And here we give some applications of this. So corresponding to the non-vanishing function, despite this mu, so this is I1 to S. S complex variable, I1, I2, this is 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 this, S belongs to natural number and involving a complex parameter, this is the mu, called the order. So it means here this can be represented into this form. This is equation number 23, and next one is this is your 24, 25, this is your 26, this is your 26. So here, if you see, this is nothing simple. The concept here we use the concept of the geometric function or basic definition of the geometric function. If you see, like 1 minus t raised to power minus lambda minus m, whatever. This is your omega. This so if 1 minus t is there, so obviously your t is less than 1. So this is remember. If t is less than 1, and because this is otherwise when t equal to 1, then it's totally meaningless. It's totally meaningless. So here we must impose the condition. This t is the less than 1. And we also to prove this one. So this is given like this. Proof of this that is given by here as equation number 29, and applying theorem 2 on 29, then we get this one, this very wonderful result, and same technique we can apply. Same technique we can apply for obtaining the other result also. Here, if you define the sequence like this, in terms of the Fermat tau hypergeometric function, like this, it is 30 as well as the 31. The geometric relation we have already discussed for true for those sequences. Clear? So now here so 30 and 31. So this is we can also obtain this is this. And further we generalize this tau right type hypergeometric function, equation number 12. This is by here. This is one parameter. This parameter defined here. So into form of the equation number 32. And provided that the series on the right hand side converges. So right hand side convergence means this is convergence, right? So if the convergence of this totally depends on the value of z also, and as well as some parameter also. So here if I put z equal to 1, z is less than 1, z is less than equal to 1, it means and we say if we say suppose z mod of z is less than 1, okay, no problem. But if we say suppose, and also we have to see the parameter this p and q. If p is equal to q plus 1 or p greater than q plus 1, p less than q, p less than q plus 1, whatever, so many conditions we can impose. So for the convergence, and we can also obtain a different type of the convergence condition here also. And apply the same methodology, one can try the analog geometric function involving this type of function. And here we give the continuous relation. So continuous relation is basically here which checks the behavior of the function, behavior of this hypergeometric right type hypergeometric function. To continuous number, it means that is the a difference by unity. If we have suppose some parameter like this alpha, it means second one will be alpha plus 1 or alpha minus 1. So between difference between these two parameters will be by the unity. By unity, it means that is 1. So here we can give some continuous relation of this hypergeometric function, and this is if number 1, first one is this. So and second one is that is given like this. Second one is this. So it means this is rho 2 plus 1, mu 1 plus 1. Okay. So this time also given the continuous relation. And proof of this also given now here. So one can try to solve those who are interested. So it means this is the proof of the theorems. And finally, we by using this these two results, one can arrive at this at the results. So in similar way, we can also derive the convergence for the different type of this hypergeometric function and right type hypergeometric function, and this is basically second one also we can use this technique to obtain the result. And this is the differential property, and we also obtain some differential property of this function. So this is given as number 1, and this is number 2 is this. This is number 1, and this is number 2. And here we give some integral properties of this hypergeometric function. So first one is this is your integral property. This can be put into form of this one. This is the first number 1, number 2, number 2. So 3 properties on number 3, and this is by imposing all this condition, then this 2r1 tau. This is your integral property. So this gives into form of this. So ultimately here we get this is your integral property. This is your integral property. And by using this technique of the integration, so we used to say this is the integral property. If you're using this one component as the differentiation, then we say this is the differential property as in our last slide. This is the differential property. So basically here we use which contain the differential differential operator. And here we have the using concept of the integration, or we can also generalize this one by using some different type of integral operator. So we can so many results can also be obtained and may be useful for the transformations. Okay. So this is the number 1, and this is the number 2, and this is your number 3. Okay. So proof of this this is the proof. Okay, this is proof of the theorem number 1, and this is the proof of theorem number 2. Proof of the theorem number 2, and no, this is the 4th property. This is your 5th property, and this is your 6th property. So here, if you see, this is a property. This is given by 1 upon this condition mode of x is greater than 1. So obviously, this is 1 upon. So here we put this 1 upon x to the power tau. So ultimately, so we have to make the balance in the sense of that our series is convergent. If series is convergent, okay. Otherwise, it will meaningless for us, and for us also, and also in the field of this mathematical sciences, because in mathematics, mathematical sciences generally we have to use only the converge series, and the 5th one is that is given into this form. This is your the 5th one is this, and here this is your 6th one. This is your 6th one. This is your sixth relation. And we give also before this this is your proof of theorem, this 4th result, and this is the 4th one, and this is your proof of the 5th one. This is your, and now seventh. This is seventh relation is this integer property. This is eighth one is this. This is your eighth one, and this is eighth one, and here if you see this is your ninth one. So 7, 8, 9. So it means here we got the, so till now these are the 9. So here again 10, 11, 12. So we obtain 10 property is this 10th one, and this is your 11th one, and this is your 12th. This is your 12th one. And we give some different relation of this function. So this function is that is defined in it, like this. This is real rho 1 greater than 0, rho 2 greater than 0, real q greater than 0, and real tau greater than 0, mod of z less than 1. Then this is given by this. So that is equal to as equation number 34. Clear? So this is one theorem and one recurrent relation of this hypergeometric function. And here we will give the proof of this theorem that is given. First, just put this. First, we have to open this one, and I'm going for some computation work. So finally, we can obtain the solution. So this is very complicated, little bit complicated solution as in 36, 37, and 38. And in the form of this first order of difference, so this is given in the form of as a 39. And this is one result. This is equation number 14. That's going to be put in the form of this. So this is also dz. So this one is there. So ultimately, this can be put in the form of this. So here we also say this is when comparing 39 and 40 and 40, and from the equation number 38 means this is your 38. This is your 30, equation number 38. So we get equation number 14. So it means substituting this equation 35, we arrive at the required differential relation 34. Okay. So this is here. And third is now succession of this property of extended tau hypergeometric function. So here we give some connection. This is very interesting results. Connection with the two R1 tau with other special function, and integer and some elementary this integer transform and the elementary integer. So here we use this due to the Fermat result. This is equation number 42, and here we use this is a Yokosuka symbol as we are discussing it at the time of starting with top. This is a new Yokosuka symbol, and this is extended gamma function is this. This is equation number 44. So here we give some relation, some other issues to function. This is connection with the modified Bessel function third type. So if rho 1, rho 2, mu 1 belongs to complex number and L3 greater than 0 or greater than 0, then this is equal to this one. This is your equation number 45. And where the alpha acts as called the modified Bessel function of the third type, which has been the following integer representation that is given by this. This is equation number 4. This is your 46. So here we can also prove this theorem, put in this 2 R1 tau, this value that is given by this, and using the formula 46, using formula 46, this is K alpha, this is your Bessel function of the third type. Formula is this. So finally, this section, this gives the required results. Ultimately, formula this, and the 47 in this and alpha x, this is given by this. So x will give the results. A connection with extended generalized hypergeometric function. This is also we can also establish a relation as mentioned in equation number 40. Equation number 48 with the condition this. This is rho 1, rho 2, mu 1, and p belongs to C, and q belongs to n. So q belongs to n. So this q is the Nelson number. This q is the Nelson number. So we can get our result in the form of q plus 1 fq. So here we can also put the q plus 1 is equal to, just like suppose if we have is equal to p. That's p fq, that is in the hypergeometric function. So this is the this is equation number 48. And where function q plus 1 fq on the right hand side, an extended generalized hypergeometric function, and this delta q semicolon rho 2 is the abbreviation for array q parameters. So this has been defined like this: p2 divided by q, p2 plus 1 divided by q, next is p2 plus q minus 1 divided by q. So this is the weakness. This all the conditions are here, and here we use this summer symbol and some property also. So this is the well-known results, and so and by using this one, and finally 46. This is this is 245, 42. So finally we can put into this form. Now we give some lemma. We will put that lemma. So this lemma will be used in our next work. So this is the difference formula for 3. This is given by 3. This is for generalized gamma function. This is into this form. So here we use this gamma function. This can be proof like this. This is basically a generalized for summer symbol hold true for this one. This is question number 49, and we use this lemma to prove the contiguous relation for extended tau hypergeometric function. So this is very important lemma for us for our proving the result. So here we will again prove the contiguous relation of this hypergeometric type function. This is this form. The first one is this, and first one, and this is your second one is this, first, second, and third one. And we will also prove, and here we can also impose the condition this rho 1 cannot be equal to 0. Rho 1 cannot be equal to rho 1 minus 1 is not equal to 0. Look at the side, because if this becomes 0, then ultimately meaningless. So we already impose this condition here. So it means here this is proof of this theorem. Upon substituting the value of this from equation number 42 and using the lemma, we get this one, and find this. So finally, this is our first result is over. Now, second one is this. Similarly, second. So here we can also use this concept. Look at the site, and further simplification. Look the result. So finally we arrive at this one. Clear? And we arrive at this one. And this is your fourth one. So fourth and this fourth lemma. This is the fourth relation. So this is also given by this. So given by this. So here if you see, this is the rho 2 mu 1 p belongs to C, and rho 1 belongs to C. And excluding this point, and real p greater than 0, tau greater than 0, mod of z less than 1, then this condition would be satisfied. And similarly here, if we take fifth one, imposing conditions are here mentioned here. So here again we obtain here we also obtain this result. This is the relation number 5. Next, we also obtain some differential property of this one. So that is experiment number 1 and number 2. Number 1 and number 2. This is given like this. Number 1 this and number 2 is this. And here in this section, in this part, we define this is in the form of some beta transform. So beta transform means, so here this, if we see this, just like your beta function, 0 to 1 is this and this. So here we treat it as this as a it is called your integer transform. So this is kernel. So this is kernel, and this is kernel has just like beta function. So it is called a beta transform. And our function is this. Our function is this. Finally, it can be written into 3R2 series. 3R2 series. This is number 50. And here this is a Laplace transform. And one can also obtain the Laplace transform. Condition we have to impose this is x upon x sigma. Mode of this is less than 1. X upon x sigma, x is to power sigma, less than 1. So if you see, so basically here this is your Laplace. This kernel is this. This is kernel e raised to power, as you know, e raised to power minus xz and into fz. dz. So it means here this is your kernel. So this is your Laplace transform, and we imposed the condition accordingly as mentioned over here. And Whittaker transform means which. So here we use the Whittaker function as a kernel. So basically your Whittaker function, and this is just like your weight function. So this is your kernel. This is your process, and give the result in the form of this. So this is your Whittaker transform. Clear? So this is your Whittaker transform. Next, now elementary integer. So elementary integer means, so here we can write this. This is about this 2r1 tau. This can be written in the form of this as equation number 53. Clear? And then this one, say you add one is this, so plus 2, and this is 1 plus f 0 f1. So ultimately, elementary function as this one. This is your 54. This is your 54 by imposing the condition, by imposing this condition. And here, this is your equation number 55. So equation number 55 is this. Okay, this one, and equation number 56 is this. This is your 56. Equation number 56 is here. So this is elementary results for 2R1 tau series. That is your right-hand extended hypergeometric function. And if I put now here p is equal to 0 in the 54, 55, 56. So 55 means, so here 55, 56, 55, 55 or 54 also. So reduces the following integer of tau hypergeometric function. So come on this side, given by this as equation number 57, equation 58 or 59. Here we use this concept of incomplete gamma function in the tau hypergeometric function, and here in the section we use for this divided into this introduction, generalized incomplete Poisson symbol, extended to complete tau hypergeometric function, which is general properties, and Mellon transform representation, connection with some other spatial functions. So here we define this one. This is your incomplete gamma function. This is equation number 60, equation number 61, and we define also incomplete Poisson symbol. Okay, this is 62 and 63. And Parmar, we send Parmar and Saxena defined incomplete generalized tau hypergeometric function as this is equation number 64, and equation number 64, and this is your 65. So here we use this is your figure. This is incomplete gamma function. The concept of incomplete gamma function. And Chaudhary and Zubair also defined the generalized incomplete gamma function in equation number 56. Oh, sorry, 66. And this is your equation number 67. So here this is started from 0 to x, and this is x to infinity. X to infinity. So this is alpha x and a complex parameter, and p is complex variable. So generalized incomplete Poisson symbol that is defined as equation number 68 and 69. And integral representation is mentioned as 70 and 71. This is extension. So we already discussed this type results in our earlier slides. And here next one is say this is represent property of this generalized incomplete Poisson symbol that is defined. So it means here first we have to impose the condition. These are the conditions. Then this can be written as equation number 727 and equation number 72. Sorry, so this is 72. This is 73. Okay, and this is your 74. This is 74, and this is your 75. And here we also obtained some different relations like this. So basically, those who are newcomer working on this, so basically this field is good for the training period, just like for the training period, and how to use some function extension, how to apply, how to use the technique, and how to put in some application form of this hypergeometric function, some different representations, some Bessels, Legendre, so many things. So this is basically for the newcomers, those very much interested or keen to join the PhD course or PhD work, so they can opt this type of work, and this will definitely help them and also develop the confidence. So this is how to start the PhD work. So this is 76 is this, and this is now 77 is this. And extended incomplete term hypergeometric function, this is given into form of 78, and this is your 79. This is your 79. And here we can also put this type form. This is by using some extension of your Poisson symbol, so or incomplete beta and gamma function. So this can be also our integral representation of this. So this gives the result 80. Similarly, 81. So here limit 0 to x and x to infinity. So basically, we find this continuity exists at the point x. At the point. So this is very interesting at the point x. And where this one is the constraint hypergeometric type function. So constraint, as you know, constraint hypergeometric type function means one parameter in the numerator, the one parameter in the denominator. So in same line, we can use this function. So this is for this are given by the Virchow. So this is the basic work of the Virchow. This is the equation number 82. If I put Virchow p is equal to 0, then you will get all this result. This one, and this is your result. And second one is here by imposing all this condition. So we will get this result. So you will get this result. And here, when I put the lambda equal to 0, so this is your lambda. When I put lambda equal to 0, the e raised to power px, that becomes e raised to power px. So that is given by this. Okay. So e raised to power px. So this has the transform. So here, so I think this, if you see px is this, and this x is replaced by t. So here we can write this is your the special case. And here we also give the proof. So that is given here. proof of this results. And further, we will discuss the differential formulas. So differential formulas in the form of 85. So here we take the k derivative of this function. So finally, after taking the k derivative, this can reduce into form of 84. This is your 84. And if a k formula here, then again this is 85. So here we are this is two type of this incomplete gamma function. So you can use this one. So this is 84 and 85. When you put p is equal to 0. When we put p equal to 0, then this becomes equation number 86. Okay, 86 as well as 87. And the Mellon transform. So here we also obtain the Mellon transform. This is by using the concept of the Mellon transform. This is given by this. So finally, we can also obtain the result. This is your this one. Okay, and next now in this section we will discuss the connection of two f1. This is two gamma. This is one. This tau is here. So that is the extension of the gamma function. So the extension of gamma function with connection with some other special functions. So here this is given into this form. So 1 minus z raised to power minus this is rho 1 and divided by rho 1. So this into gamma rho 1 into x 1 minus z, and this semicolon p 1 minus z. So here we can put this result. Here we can put the one result. And taking the substitution of this, so we can this is t 1 minus z equal to u. So we will get this result 1 into x 1 minus z, and this is equal p 1 minus. So we very interesting results. So basically, this is some connection with some other special functions. So this is our duty to explore the possibility. So here this can be put in the form of this. So this is your error complementary function, and this can be written like this. Okay, and this can be also put into this form. This gamma is here. So half xp semicolon p gamma minus half xp. This is given by this. So it means this is given by this. Ultimately, here we can write a. Finally, we obtain result. This is e raised to power minus 2 under root p, and the gamma 1 upon 2u, and this is your e square under root p, and gamma 1 upon 2, this is gamma 1 upon 2p. So this is these two results. Very interesting results. This one, but related with some calculations and connection with the complementary array function. So, and this is your first one is this. This is for the connection with extended incomplete gamma function, and connection with complementary array function. So this is given by this one, and similarly this one. Connection with complete hypogeometric function, and this is complete hypogeometric function. Clear? These two. And next now, this is a connection with the incomplete gamma function. So this can be also put in the form of this is fourth one that is given by this. This is the fourth one, and one relation is given like this. So here again, if you see, so e raised to power minus 2 here, you will see it's minus 200 p there. Okay, and this is in the form of this. So here error function under root xz under root p upon under root x, and here we will get the put in form here collected incomplete gamma function. So this is gamma 1 upon 2u, as well as here this is the same thing. So in same technique, so it becomes the 1 upon 4 minus 4 under root pi p, and into this one. Next one is next slide. This is extended Poisson symbol and associated extended hypergeometric function. So here we also extended the Poisson symbol and tried to associate with some extension, with extended hypergeometric function. In this section, we will discuss the introduction, extended Poisson symbol, and this is extended hypergeometric function and the properties, integer transform, generalized integer transform, generalized fractional operator. This is very interesting result, and modified fractional calculus approach. So extended this gamma function is given by the Jumari as 89. Here they use the concept of the meters of a function. This is 90 and involve the fractional integral with respect to this. So basically these results are, we use this is sometime in if you go some mathematical some in group of the mathematics, some are agree or some are not agree about this result, and according to them, I received the feedback that this result may be useful in the case of in applied mathematics, but we cannot claim these results are very positive for this your pure mathematics. So one can use in the applied mathematical form. So many work are still going on for finalizing this result, whether it is 100% correct or not. Whatever. So he generalized some this is the Poisson symbol into this form is 92. Okay, and this property Poisson symbol is there. So this also have the properties like this. First one is this. This is the second one is this, and this is the third one. This is your fourth one. This is your fifth one, and this is the sixth one. So if you go and read the Renville book, and you will get so many theorems so related to this, and here we simply extended all the results by using the concept of the Jumari. So first now the extended Gauss hypergeometric equation. So earlier as I discussed that initially about the Gauss hypergeometric function, so that has been defined. And so here we extended by using this concept of the Jumari. So we introduced by alpha. So this alpha is here, one can easily see, and it is defined like this. So this one already we discussed. This is a Poisson symbol, and here this extended hypergeometric function with Q numerator and the Q denominator. So this is our results are here by this is rho 1 and alpha. So due to this alpha, it has been some property has been changed. So it means now here this is conditions are given for the convergence condition of the said hypergeometric. This extended Gauss hypergeometric function is given here, are given here. This is like the first one is this one for a finite value of z. The second one is convergent for mod of z is less than this one. Divergent for the and gamma z, mod of z equal to factorial alpha whole raised to power minus 1. This is you can say 1 upon factorial alpha. So convergent condition is this one. This is the convergent condition, and next one is this is. So this here z is not equal to 0. So here we use this result. We obtain the differential equation by using the concept of the contiguous relation and this operation technique. So theta, if we assume theta is equal to z, d dz, and we got this property. So here this is your hypergeometric function. So using this hypergeometric function, so it means we will get this one. And so thus we can say this differential operator omega. This is omega is equal to this is 2f1 with this parameter alpha. So finally we got this result. This is 95, and this can be the final, and this can put in the form of this. So this is a type of, if you see, this is nothing simple type of the extended type of the hypergeometric function. But here we, by doing this alpha, here if you can say in equation, you can see equation number 96. this is a factorial alpha. Okay, so factorial alpha is equal to, if I keep factorial alpha is here, so then what will happen? So it means here, if suppose this is your 1, so ultimately you will get 1 minus that, and this is your omega double dash. So this is second derivative of the equation. So second derivative of the this omega. So finally, it means this is a type of the hypergeometric function. Hypergeometric function. Now, and we get similar equation for this one. In the equation where this is the sigma n given into this form, and this was apply all the technique. So we can get this differential equation in the form of this alpha, this into in the form of this. This is your 97. This is 97. And that's now transformation. So here we use the iron type transformation. Iron type transformation. This is our Newton hypergeometric function, and so we prove this theorem like this. This is clear, and finally we got this one. No. Finally we got this one. So it means 1 minus factorial alpha into that whole raised to power minus rho 1, and into this is our new extended hypergeometric function. So this is equation number 100. And a second one we go for equation number 98. 98 is this. So this is a corollary of the 98. So this can be also can be written, and so if I take some substitutions like this, so we can also obtain the result. This is your 102. And this is our theorem. This is our theorem. This is your 103. And if alpha is equal to 1, then we will have this one 2f1 minus n. This is rho 2f. This is your equation number. This is your 104. Equation 104. So this is 104. So it means this is we are the proof of this theorem in our result. So this is 1, and this is your, we have the finally we arrived at this is 105. So by comparing the coefficient of this two series in 105, we reached to the desired result 103. And here we also obtained some Mellin-Barnes integral, Mellin-Barnes equation. This is the equation number 106. By imposing all the conditions, these conditions are mentioned over here. And here we also again try to obtain some differential property of this type hypergeometric function. So that also be satisfied if in the form of 107, and this is 107, this is 108, and this is your n derivative. So basically this is your n derivative, and here again this is your n derivative, and finally this is 109 and 110, and these are the proof of the theorem. These are the proof of the theorem. This is 111, and which gives gives 107. So 107. This is your 107. Okay, 107. And different form of 10 is by applying the corollary of the transformation. By applying the corollary to the transformation form on the one, this is 107. And this is the third one. Third result is this, in the form of 112 and 113. This is, and the next one is this is your 114. And the integral transform. So here we also discuss some changes in generalized integral transform that is given in the form of 115 and 116. And here the proof of the theorem. This is basically some proof. So proof of the theorem. This is given into this form. Here the proof. And Mellin transform of the representation can be written as a 117, and here we also obtain the vertical transform representations of this function. This is given into this form, geometric transform, and this is your next result. This is the use of the we will use this one to prove the theorem, and this is your K transform. K transform is this, so it means K transform representation, and this is your Laplace transformation of this function. This can be finally we get the finally we obtain this result. And beta transform, so we get this one. And generalized integer transform. So here we will give some model in 2012. What I'm going to do is generalized Laplace transform and generalized Hysterresis transform. This spelling is wrong. Hysterresis transform. So generalized Laplace transform is given by this. This equation number 1 to 1. This is the generalized Laplace transform, and here like 1 to 1 and 1 to 122. And she also imposed a condition. This is tau beta generalized hypergeometric function of 21. So this is F1 F1. This is tau beta. Basically, this is some content hypergeometric type function. So this can be put into this form. And this is your result. This is so it means PF generalized type function. This is defined like this. Okay. So to say here 1F1 and here PF2. So it means 1F1 means it means one is in denominator as 1. This one is in this one in the numerator. So finally, and here she also gave the generalized Hysterresis transform. We saw here we also use that generalized Hysterresis transform. And that which I got the result this 124 as well as 125. And this is again the one theorem. So this is your extension of this Laplace transform. So this is here this is our function. So this gives you equation. This is 126, and the value this to the sigma 1 y that is defined by this. So if I put this is your gamma 1 equal to 1, so this equation becomes into 127, and here this is your 128 is this, where the sigma 2 bs this can be represented into form of this one. So here also some generalized some transformation. This is some proof of this for result. This 129, 130 like this. So this is our. Now this is the next theorem. One theorem is this is what in the form of this 131 with all this condition. This is 131, and with where this is the sigma 3 bx that is defined by this. So here this is 3 side is defined into this form, and this is 132 is this, where this is sigma 4 bx that is defined by this. So from the reference of generalized Hysterresis transform, generalized hypergeometric function, and changing the variable from x upon y equal to t, then and this t is this, and t gamma 1 this is equal to u in the integer involved, and then one can get our result. One can get the result one, and which is equal to this. And here we also use some fractional operators and this function. So this is our generalized hypergeometry function. So fraction by using the fractional operator. So this is what finally theorem is this. We proved this theorem, and conditions have been imposed here like this. So finally, this is the result, and if this condition takes a second one, so finally we also obtain this equation, this 134. And similarly, so here in the open up the function due to the cycle and the made equation of 14, this is given as this one, and 136 equals to 136, and here F3, what is F3? F3 is your Apple third function, known as the horn function. Apple function, this is also known as horn function. So using this formula, so this one, so finally we obtained our the result. This is the proof of the theorem. And similarly, this for the second the results, we also got this one. This one. Next one is this is 138. This is 139. And here we use generalized fraction derivative operator, which are defined like this. This is 140 and 141. So this is this can be given into this form, this one as well as this form. So clear. So for that, simply give the result. So if I take alpha is equal to 1 in the theorem we have discussed in this chapter, it's in this talk. So we get the corresponding result of classical hypergeometric function 2f1 as well as pf. Here we use some modified fractional calculus approach. So here we also use the geometric concept to obtaining the result. So this is in the form of the theorem. This is a theorem 144, and this is 145. This is theorem 144. This is for 144, and this is this result. This is well known. One can easily obtain this result, and here this we give one theorem based on the geometric work. That's the integral of this with respect to dx alpha. So here, if I put the alpha equal to 1, so alpha equal to 1 the symbol you will get that ordinary this is your Gauss hypergeometric series. So imposing the condition, here this can be put as equation 146, 147. Okay, and so these conditions are given here now. This is your 140. Next, now this is theorem beta. This fractional Laplace transform of this. So this can be given as 149, and this is our this is where the conditions are here, and like this. So these are the conditions, and we define this L beta is this. So it is into form of this. So basically, here the form of this, these are nothing simple and Mitchell's Leffler function. And this is now asymptotic extension of the extended concurrent hypergeometric function. So here we use the concept of the concurrent hypergeometric function. So this one, this is our if you take the integral into this form, basically if you see this is nothing some just like e to power minus z dt. So this is a type of some your Laplace transform type. So in Laplace transform we have the limit 0 to infinity, but here we use like this minus z dt. So after, so here simple we use this we change this, and Gujrat defined by this 150, where this is 152, and this is extended concurrent hypergeometric function. This is a concurrent hypergeometry. As we earlier discussed, this is in the case of the Gauss extended hypergeometric function, whatever. So this is we put in the form of this 154, and we can also use this result in the form of some Gauss type hypergeometry. We can extend this result, and so here, but here we are only concentrate for the hypergeometric function and try to skip all this calculation. So this is simple form of the integral that is given 155. And here we get two cases, some cases of this this asymptotic extension of this. When case 1, this is given, first case given by this factorial alpha z plus a plus 1 minus b greater than 0. On that case, we get the 156, this one. And second one, when this is the less than 0, so we get this is your 157, and this is your 157, and this is your third case, when equal to 0, then we get the 158. And these are the proof of this theorem. Proof of the theorem. So conclusion in the future scope for basically those who are interested to study in the hypergeometric extension, the hypergeometric function. You find this is what in the terms of this function we have provided extension usually property of the hypergeometric and current hypergeometric function. Therefore, results presented here give some more contribution to the theory of the special function. And so the function we have extended contain many of the family of special function and the subcases. This extension are expected to prove to be useful, and for the further work or future work, we can extend the family hypergeometric function, current hypergeometric function can be defined in more than one variable, and generalize of this function can be established. With the help of extended the Poisson symbol, lambda and alpha, various other family of the special function can also be generalized. And here, these are the references. These are the references. Thank you. Thank you, Dilip.